Have you ever wondered how a spacecraft that is already moving at several kilometers per second along a path determined entirely by gravity manages to change where it is going without roads, without steering wheels, and without the kind of direct mechanical feedback that makes navigation on Earth feel natural and intuitive? The problem seems straightforward until you realize that orbital mechanics operates under rules that are almost perfectly inverted relative to everyday experience. In orbit, firing your engines to go faster does not make you go faster along your current path. It changes the shape of your path in ways that carry you to a completely different altitude, where you end up moving more slowly. Firing your engines to slow down does not simply reduce your speed along your current orbit. It drops you into a lower orbit where you paradoxically end up moving faster and changing the direction your spacecraft is pointing, which is how steering works in every other vehicle humanity has ever built. Accomplishes almost nothing useful in orbital navigation unless it is precisely coordinated with a timed engine burn of exactly the right magnitude. Understanding how spacecraft adjust their trajectories in orbit requires setting aside every intuition built from driving, flying, or sailing, and replacing those intuitions with a way of thinking about motion that was first described mathematically by Johannes Kepler in the early 17th century and explained physically by Isaac Newton shortly afterward. A framework that feels deeply alien at first contact, but that reveals with patience one of the most elegant and internally consistent descriptions of motion that physics has ever produced. The starting point for understanding orbital trajectory adjustment is the concept of orbital energy, which is the quantity that actually determines what orbit a spacecraft is in at any given moment. Orbital energy is the sum of the spacecraft's kinetic energy, which depends on its velocity, and its gravitational potential energy, which depends on its distance from the body it is orbiting. The critical insight is that this total orbital energy is conserved in the absence of propulsion, which means that as a spacecraft moves along its orbit and its altitude changes, its speed changes in a precisely determined way to keep the total energy constant. When the spacecraft is at its lowest point in the orbit, it is moving fastest because its potential energy is lowest, and all of that energy has been converted to kinetic energy. When it is at its highest point, it is moving slowest because its kinetic energy has been partially converted back to potential energy. This continuous exchange between kinetic and potential energy is what keeps a spacecraft in orbit without any propulsion, and it is also what makes the effects of engine burns so counterintuitive. Adding energy through a burn does not simply speed up the spacecraft at its current altitude. It permanently changes the total orbital energy and therefore the shape of the entire orbit, with consequences that propagate around the full trajectory. The prograde burn is the most fundamental orbital maneuver and the one whose effects most starkly illustrate the counterintuitive nature of orbital mechanics. When a spacecraft in a circular orbit fires its engines in the direction of its motion, the prograde direction, it adds kinetic energy to its orbit and increases the total orbital energy. At the moment of the burn, the spacecraft is now moving faster than the circular orbital velocity at that altitude, which means gravity is no longer strong enough to keep it in the circular orbit. The spacecraft begins to climb outward, trading kinetic energy for potential energy as it rises. The orbit is no longer circular but elliptical, with the burn point as the lowest point of the ellipse and the opposite side of the orbit rising to a new maximum altitude, called the apoapsis. The spacecraft coasts along this ellipse, slowing as it rises, reaching its minimum speed at the apoapsis, and then falling back down toward the burn point where it reaches its maximum speed again. The entire ellipse repeats indefinitely unless another burn is performed. The key insight that makes this so counterintuitive is that the spacecraft ended up higher and moving more slowly than before the burn, even though the burn added energy to the system. The added energy went into raising the orbit, not into sustaining a higher speed at the same altitude. The retrograde burn, which is a burn in the direction opposite to the spacecraft's motion, has the mirror image effect. It removes energy from the orbit, lowering the apopsis on the opposite side of the orbit from the burn point and placing the spacecraft on an ellipse that dips lower than the original circular orbit on the far side. If the retrograde burn is large enough to lower the far side of the orbit into the upper atmosphere, the orbit becomes one that will eventually lead to re-entry, and the spacecraft descends in a controlled spiral rather than remaining in orbit indefinitely. This is the principle behind the deorbit burn that ends any low-orbit mission. A retrograde burn that removes just enough energy from the orbit to lower its lowest point into the atmosphere, allowing aerodynamic drag to complete the deceleration and bring the spacecraft down. The precision required for a deorbit burn is considerable. Too small a burn leaves the spacecraft in an orbit that decays slowly over many revolutions, while too large a burn results in a steep re-entry that generates excessive heating and deceleration forces. The Hohmann transfer uses the prograde and retrograde burn concept to move a spacecraft efficiently from one circular orbit to another circular orbit at a different altitude. And it is worth examining in detail because it illustrates how orbital maneuvers are planned and executed in practice. The maneuver begins with a prograde burn at the starting orbit that raises the apoapsis of the orbit to the altitude of the destination orbit, placing the spacecraft on a transfer ellipse. The spacecraft then coasts along this ellipse with no propulsion for half an orbital period, traveling from the burn point at the low end of the ellipse to the apopsis at the high end. At the apopsis, a second prograde burn circularizes the orbit by adding the velocity needed to match the circular orbital velocity at the new altitude. Without this second burn, the spacecraft would simply continue along the transfer ellipse and fall back down to its original altitude on the next half orbit. The efficiency of the Hohmann transfer comes from performing each burn at the point in the orbit where the spacecraft is moving fastest relative to the destination, which maximizes the energy gained per unit of propellant consumed through the Oberth effect. Any other combination of burn points that achieves the same orbital change requires more total propellant. The bielliptic transfer extends this principle to situations where the destination orbit is very much larger than the starting orbit, and it demonstrates one of the more surprising results in orbital mechanics. That for sufficiently large changes in orbital altitude, a three-burn maneuver that goes first to an intermediate orbit much higher than the destination and then comes back down is more fuel efficient than the two-burn Hohmann transfer that goes directly to the destination. The explanation lies in how the Oberth effect distributes its benefits across the burns. In a Hohmann transfer to a very high orbit, the second burn at the higher apoapsis has to add a large velocity increment at a point where the spacecraft is moving very slowly, which is inherently inefficient. In the bielliptic transfer, both the first and third burns are performed at points where the spacecraft is moving much faster, making better use of the Oberth effect even though the spacecraft has to travel to an intermediate orbit that is higher than the destination. The crossover point where the bielliptic transfer becomes more efficient than the Hohmann transfer occurs when the ratio of the destination orbit radius to the starting orbit radius exceeds approximately 12. And for very large ratios, the efficiency advantage of the bielliptic transfer becomes substantial. The plane change maneuver, which alters the inclination of the spacecraft's orbit relative to a reference plane such as Earth's equator, is the most propellant expensive type of orbital adjustment, and the one that most clearly demonstrates why the geometry of the initial launch trajectory is so carefully chosen. Changing orbital inclination requires applying a delta V perpendicular to the orbital plane, and the amount of delta V needed depends on how much inclination change is desired and how fast the spacecraft is moving at the moment of the burn. Since orbital velocity at low Earth orbit is approximately 7.5 kilometers per second, changing inclination by even 30 degrees requires a delta V of nearly 4 kilometers per second, which is more than half the total delta V needed to reach low Earth orbit from the ground in the first place. A 90-degree inclination change at low Earth orbit would require more than 10 kilometers per second of delta V, which exceeds what most spacecraft carry for their entire mission. This is why it is so much more efficient to launch a spacecraft into the correct inclination from the ground, where the launch vehicle provides the inclination setting velocity essentially for free as part of the initial ascent, than to launch into a convenient inclination and correct it in space. The rendezvous problem, which involves bringing one spacecraft from its current orbit into proximity with another spacecraft in a different orbit, is operationally one of the most demanding trajectory adjustment challenges in human spaceflight. The fundamental complexity is that two spacecraft in different orbits are not simply at different positions in space. They are in different dynamical states, following different orbital paths that are completely determined by their respective energies and angular momenta. And the only way to bring them together is to change the orbit of one until it intersects the orbit of the other at a moment when both spacecraft are simultaneously at the intersection point. The challenge is compounded by the fact that orbital maneuvers change the orbital period as well as the orbital shape. So a maneuver that raises the apoapsis to intersect the target orbit will also change how long it takes the chasing spacecraft to complete each orbit, shifting its timing relative to the target in ways that have to be carefully calculated and controlled. The solution requires a sequence of maneuvers that simultaneously adjusts the shape, size, and phase of the chasing spacecraft's orbit to bring it to the same point in space as the target at the same moment in time. And executing this sequence correctly requires precise knowledge of both spacecraft's positions and velocities at every step. The phasing maneuver deserves particular attention because it illustrates one of the most counterintuitive aspects of orbital rendezvous. Catching up with a spacecraft that is ahead of you in the same orbit requires slowing down, not speeding up. If two spacecraft are in identical circular orbits, but one is ahead of the other in the orbit, the trailing spacecraft cannot fire its engines in the prograde direction to catch up, because a prograde burn raises its apoapsis and puts it in a larger orbit with a longer period, causing it to fall further behind relative to the leading spacecraft. To catch up, the trailing spacecraft has to fire its engines in the retrograde direction, lowering its orbit and reducing its orbital period so that it completes each orbit faster than the leading spacecraft. Over successive orbits, the trailing spacecraft gains on the leading spacecraft and eventually laps it. The timing of the subsequent burn to raise the orbit back to the target altitude has to be calculated precisely to ensure that the chasing spacecraft's orbit intersects the target's position at exactly the right moment. Getting this timing wrong by even a small amount results in the chasing spacecraft arriving at the target altitude slightly ahead of or behind the target, requiring additional maneuvers to close the remaining gap. The gravity assist maneuver is a trajectory adjustment that requires no propellant at all, but that depends on precise navigation to execute correctly. When a spacecraft passes close to a planet or large moon, The gravitational field of that body accelerates the spacecraft as it approaches and decelerates it as it moves away, resulting in a change in the spacecraft's direction of travel, but no net change in its speed relative to the planet in the planet's own reference frame. However, because the planet is itself moving through space at orbital velocity, the gravitational interaction that changes only the spacecraft's direction relative to the planet can change both the speed and direction of the spacecraft relative to the Sun, effectively transferring momentum from the planet to the spacecraft. The size of this velocity change depends on how close the spacecraft passes to the planet and the geometry of the flyby relative to the planet's orbital velocity. And planning a gravity assist requires calculating the required flyby trajectory with sufficient precision that the spacecraft passes at the correct altitude and in the correct direction to achieve the desired velocity change. Multiple gravity assists can be chained together to achieve velocity changes that would require prohibitive amounts of propellant to achieve through direct burns, which is why the most ambitious missions to the outer solar system have used years-long sequences of planetary flybys to gradually accumulate the velocity needed to reach their destinations. The low-thrust trajectory adjustment performed by ion propulsion systems represents a fundamentally different approach to orbital navigation than impulsive chemical burns, and it produces trajectories that look qualitatively different from anything achievable with chemical propulsion. An ion engine produces thrust that may be thousands of times smaller than a chemical engine, but can sustain that thrust continuously for months or years, gradually accumulating velocity changes that far exceed what a chemical engine could achieve with the same propellant mass. Rather than a sequence of discrete burns separated by unpowered coasting arcs, an ion-propelled spacecraft follows a continuous spiral trajectory that slowly evolves its orbit over weeks and months. The mathematics of optimizing these continuous low-thrust trajectories is considerably more complex than the impulsive maneuver calculations used for chemical propulsion, requiring numerical optimization techniques that search through the continuous space of possible thrust directions and magnitudes at every point along the trajectory to find the sequence that achieves the desired final orbit with minimum propellant consumption. The results of these optimizations are often trajectories that spiral outward or inward in complex patterns that bear little resemblance to the clean elliptical arcs of chemical transfer orbits, but that achieve their objectives with a fraction of the propellant mass that chemical propulsion would require. The autonomous execution of trajectory adjustments without real-time ground control has become an essential capability for spacecraft operating far from Earth, where communication delays make ground-commanded maneuvers impractical. A spacecraft at Mars is between 3 and 22 minutes away from Earth by radio, depending on the relative positions of the planets, which means that a round-trip communication for a single command takes between 6 and 44 minutes. Executing a precisely timed maneuver under these conditions requires the spacecraft to carry out the entire maneuver sequence autonomously based on pre-uploaded commands and its own onboard navigation measurements. Modern spacecraft carry sophisticated onboard navigation software that can determine the spacecraft's position and velocity from optical measurements of stars and planetary bodies. Compare the measured state to the planned trajectory. Calculate the corrections needed to bring the trajectory back into alignment with the mission plan, and execute those corrections autonomously within the constraints of the onboard propellant budget and the structural limits of the propulsion system. This level of autonomous capability is not a convenience feature. For missions to the outer solar system or to small bodies where the navigation geometry changes rapidly during close approaches, it is an absolute operational necessity. What the complete picture of orbital trajectory adjustment reveals is that navigating in space is an act of working with the physics of gravity rather than against it, of understanding how energy flows between kinetic and potential forms as a spacecraft moves through a gravitational field, and of applying precisely calculated impulses at precisely chosen moments to redirect that energy flow in the desired direction. Every maneuver a spacecraft performs changes not just its current state, but the entire future trajectory it will follow for as long as no further maneuver is applied. And the skill of orbital navigation lies in choosing maneuvers that redirect this future trajectory toward the desired destination while consuming the minimum possible amount of the propellant that is always the scarcest and most consequential resource on any space mission. It is a discipline that rewards deep understanding of the physics over intuition, that produces solutions that frequently look wrong from the perspective of everyday experience, but that are exactly right from the perspective of Newtonian mechanics. And that has made possible every crewed mission, every planetary probe, and every Earth-observing satellite that humanity has ever operated. In the elegant curves and precise timing of orbital maneuvers lies not just engineering achievement, but a demonstration of what becomes possible when human intelligence fully comprehends and works in harmony with the laws that govern motion in the universe.